Welcome to another tutorial in monitoring of forest resources. My name is Lutz Fermann and we are here again in the lecture room because today I'm going to talk about some basic steps we need to go for analyzing data from a forest inventory. As an example, we take data that were collected by students in the last summer term. We have a very small forest area behind the campus, and in this area we conducted a forest inventory in a systematic grid. The students assessed nested circular sample plots and took the typical measurement on single trees like diameters, tree heights, tree species and other variables. We will now have a look on this data, and together we will go through the basic steps of data analysis on my computer. Okay, let's do some data analysis with the data that have been collected in the field. I'm using Excel 2019 here. You can do everything also in R if you are more familiar, but the calculations we need to do are very simple and we can do everything with Excel. First of all, I like to connect to the data that I have exported from Collect Desktop. For this demonstration, I have exported data in Excel format, so I have Excel workbooks containing my data, and in fact I like to query these original data in order to do some calculations. So since I even don't like to see the data in my table, I just like to do some analysis. I don't like to mess around with my data in Excel. I just need to create queries or connections to these original data sources. I have 4 tables here which are not related with each other up to now. A plot table, a tree table and some other table, and I like now to import or connect to these tables. Let's start with the plot table, and if you import this table, then you can select different options on how to do that. If you just load the data, you will establish a table in this workbook, but I don't like to have this. What you can also do is you can load this data in the background and also add this data to a data model, and this is exactly what I like to have. But before I do this, I still like to do some small edits on the query that I'm defining here. So if I open this, then you see the query editor in Excel, which is a very powerful tool to query huge amounts of data. We are only looking at 20 plots, and the only thing I like to change here is the name of this query. Since this is my plot data, I also like to call it plot. I can do many different things here, but at the moment I just take the data as it is, and instead of loading it as a table, I like to load it in the background and just include it in the data model. So I only create a connection to my original data, and I like to add this to the data model of this workbook. If I do this, then the query is executed, and you can now see that 20 plots have been loaded, and what is still missing now is the tree data. So in the same way, a little bit faster because you already know how it works, I will now define the query to get or to load the tree data into my data model. Also here I just change the name of this query and I load this in the background by only creating a query to this data. You see that the Excel workbook that I'm working in is still empty, so we don't see any tables, any numbers here. We have loaded something in the background, and the next step would be to relate these two tables. Up to now they are independent of each other, but later we need to know which tree comes from which plot, and therefore we need a relationship between these two tables. Different options to do that. We can establish relationships manually here. What we can also do is we can open the data model. So if I go here, then a new dialog will open. You have a new user interface here that gives you access to the data model that is now behind Excel. You see that we find two tables here in this data model, the plot table and the tree table, and this is where our data queries are, and this is also the place where we can do calculations and where we can also relate the data. To relate the data, we can switch to the diagram view. If we do this, then you see these two tables or these two queries that we have imported here, and you also see the different variables here on the plot and on the tree level. And what we need to do now is we need to relate our tree table with the plot table, and we can use the plot ID number as the key field here. So you can drag and drop and connect the plot ID in both tables, and this is how we can establish relationships between these tables. If you go back to Excel now by minimizing this data model, you still see nothing here. But what we can do now is we can test whether this relation works. For this purpose, I like to insert a pivot table. Most of you probably know pivot tables. These cross tabulations are very useful to aggregate data on different levels and to slice and filter your data on different levels. And if we have a data model in the background that is connected to queries and data, then we can also create a pivot table over these queries. So if we open or if we insert a pivot table here, then the usual way how we work with such a pivot table is that we drag and drop some variables or categorical variables in the rows field, in the columns, or in the values. What I like to do now, just as a short test, I like to see in my rows all the plot IDs from my plot table, and I like to aggregate some value from the trees on each of these plot IDs. Since we have not yet implemented any fancy estimators, I can do a simple count of the trees per plot. So let's count some field from the tree data. I take the tree ID here and I put it in the values field. And the default aggregation that Excel is using here is a sum. So I'm now looking at the sum of the tree ID per plot, which doesn't make any sense. However, I can change the aggregation here and I can also select a count. So if I switch to a count, I get a first overview over my data, and this is now just the number of trees that have been measured on all of these different plots. Altogether 284 trees have been measured by the students. Okay, this is nice and interesting, but this is not what we want to have. What we need at the end are some estimates of target variables. And let's take one of the typical target variables as an example. Let's say I like to estimate the average basal area per hectare from these 20 plots that I have distributed in this forest area. Therefore, I need to do some calculations on the level of single trees. First of all, I need to know the expansion factor of each single tree. And secondly, I need to calculate the basal area of each single tree. But where to do calculations if there are no data in my table? So we can do these calculations directly in the data model. So we can switch back to the data model. And here we can switch to the data view. So we can have a look on our data now, the plot table and the tree table. And what I want to do now is I want to switch to the tree table. And I like to calculate something here on the level of single trees. The first essential calculation that we always need to do is to determine the expansion factor of each single tree. In our case, we used a nested plot design. We had nested concentric circular sample plots with different plot sizes for different diameter ranges of trees. And that means we have an unequal probability plot design where trees of different diameters have different expansion factors. So we have the dBH here, so we know the dBH of each tree, and we can use this to find out which plot area should be considered for expanding this value, this observation, to 1 hectare. We just need to implement a simple if statement. So we can say if the tree dBH is smaller than 15 centimeters, then we used plot area number 1, and this is a placeholder now. I will substitute this later. And if the tree dBH was smaller than 30 centimeters, then we used plot size number 2. And if the dBH was larger or equal than 30 centimeters, then we used the largest plot size. And this is what we then also need to consider for expansion. So I have just executed this formula, and now we have a result here, which is just the plot area or an indicator for the plot area that should be considered for upscaling. Somehow we need to substitute now these 1, 2, and 3 by the correct expansion factor, and this expansion factor is a result of the plot size and how many plots of this size would be needed to fill 1 hectare. So in fact we need to divide 1 hectare in area, and this is 10,000 square meter. So 10,000 square meter divided by the plot area, and the plot area can be calculated by pi times the radius of the plot. In this case it was 3.14 meter to the power of 2. So we are here calculating the plot area, and then we calculate 10,000, so 1 hectare divided by this plot area. And we had another radius for the bigger trees, so I can just copy this and also use it here. And I will also use it here. If you cannot follow, don't be afraid, this is nothing special here. So the second largest radius was 7.98 meters, and the largest circle we used in our plots was 12.62 meters, which is an area of 500 square meters at the end. If I execute this, then I now get the correct expansion factor depending on the diameter of the tree. If the tree is bigger than 30 centimeters, then the plot area is 500 square meters and the expansion factor is around 20. And for smaller trees it is a higher expansion factor. So we can also give a name to this new calculated field. We can call it expansion factor, but in fact it is nothing else than the number of trees per hectare that is represented by each tree in our sample. So let's call it N per hectare. Based on this calculated field, we would now be able to estimate tree density per hectare in our pivot table. But as I said before, I like to estimate the mean basal area per hectare. For this purpose, I first need to calculate the basal area of each single tree, and I need to expand it by this expansion factor here. So how to calculate the basal area of a single tree? Pi divided by 4 times the diameter of the tree, so times dBH to the power of 2. This would now give us the basal area in square centimeters, which is maybe not nice because usually we want to have it in square meters. What we can do here is we can divide the diameter by 100 to get the result directly in square meters. And we see a small error here, and this is probably because I have not selected the right DBH here. Okay, so, and there is still an error because I have not used the right function for pi here. I hope I solved all the problems now. What you see now is the basal area per tree in square meters. If we like to have it per hectare, we need to multiply it with this expansion factor here. So what we can do is we can select the expansion factor and multiply the basal area of each single tree to come to a predicted value here of basal area per hectare. And we can give a name to this variable. Let's call it basal area per hectare. And now this is probably enough for a short example. We can now minimize our data model and go back to Excel, and what you see now is that in our tree table we have these new calculated fields that we have just implemented in the data model, so in the background. There is no other table, no other data that you see here. Yeah, let's just drag and drop these fields into the values field here of our pivot table. In this case, the default aggregation of a sum is absolutely correct, because what we are doing now is we are summing up all the trees per plot, or summing up the target value here per plot. So what we get here is already an estimate of the basal area per hectare and the number of trees per hectare for each single plot. From this data we can now go on, and this is now a workaround, and this is not a very nice technique. I will show a much better technique in a moment. But we can use now these observations on the level of all the single plots as a basis for further calculation. For example, of a mean, an average of these values, for example, or a variance or a standard deviation or whatever. So this is nice, and we can do it like this. However, it would even be nicer if we have this calculation as a measure that we can also use here in our pivot table at any position. And this is something that I can show you in a moment, or at least give you a very short hint how to do that. So this is now our estimated mean basal area per hectare, and this is the mean number of trees per hectare from these plots. In the same way, you can also calculate the related statistics and confidence intervals. If we like to implement an estimator that we can use like a function that is recalculated every time when we set a filter or slice the data, we can implement something that is called a measure. Such a measure, if you make a right click here on one of these tables, allows you to formulate a function that is executed on every level of filters or slices that you have in your data. And this is something that makes a pivot table even more efficient and more useful than the simple aggregations that I showed you here. And I will give a very short example of how an estimator would look like in this very, very simple basic example. So let's assume we like to estimate the mean basal area per hectare. Then we need a different syntax here. It is not the standard Excel formulas that you already know, because we are working here in a different domain. What we like to calculate here is an average, and without too much explanation about the syntax, we like an average over the plot values, over the values that we have aggregated per plot. So first we like to calculate a sum of the single tree values. Let's say the basal area per hectare that we have computed for every single tree. And from this calculated sum per hectare, we like to calculate an average over all our plots. Let's see whether this is working. And we like to get this as a decimal number with 1 digit, for example. And if we implement this, then you see that you get a new field here. And you also see that it has a slightly different format, because this is now a function that can be computed over every filtered subset of data that you can imagine. So I drag and drop this also here into my values field, and you see that the values on the single plot level are exactly the same as the ones we have calculated before, but down here, instead of a sum, we now have an average, and this is exactly the average that we can also calculate over these plot observations. So what we now have is already the final result that we like to have. It is now just an estimate of a mean and not of a variance or a standard error, but you can imagine that this can be computed in similar ways. And if we look at this estimator now that we have implemented, and we would slice our data using, for example, the species code of the single trees as an additional filter, then you can see that this measure is now computed for every single tree species separately. We also don't need the plot ID anymore. We can take it out and we can filter for any other variable, like, for example, the canopy layer that we have used in the field. And also here you see that everything is then computed for this new filter or slicer. So in fact, what I wanted to show you is that there are some smart technologies to implement estimators also in Excel. And it's just a matter of thinking carefully what you like to do with your data. You see that we have no data still in our data sheet, we only have results, and this is exactly how our data should look like. If we like to change something on the original data, we should do it in our original tables, but we should not mess around with the data. Okay, I hope now you get a certain understanding of the basic steps we need to do if we like to analyze forest inventory data. This was a very basic and simple example of only 20 plots. However, you can upscale this to several hundreds or even thousands of plots in a larger project area. The systematic of calculation is always the same, even if we can imagine much more complex estimators and statistics if we use other sampling designs. Thank you for watching up to here, and see you in one of our next tutorials.